Hello and welcome. I'm Henry Yang. Here at Lyft, I lead the transient data team. We're responsible for the infrastructure of non-persistent data. And of course, we use a lot of Redis. Today, I would like to share with you some new features that we have built into Envoy Redis proxy and how we use those features for our migration story. And then I would like to share some experience of building auto-scaling Redis clusters. Then we would like to revisit the scenario of using Redis as a cache. Before we jump into all the details, I would like to share with some context with you. Previously at RedisConf 2017 and 2018, we share our journey in migration from Twin Proxy to Envoy Redis proxy. In both of these approaches, we are sharding the data across a cluster of independent Redis nodes. The sharding decision is distributed to independent Envoy processes with no coordinations. This maximizes availability but no consistency. Fast forward 2 years, the number of Redis clusters exploded at Lyft. Some new use case requires improved consistency guarantees. Other cases have new scalability challenges with the old approach, where we want to independently scale reads and writes. When we want to talk about the Redis cluster infrastructure at Lyft, it's hard to avoid talking about Envoy, specifically Envoy Redis proxy. As many of you know, Envoy is a popular and widely used open source project. It is basically a sidecar proxy that is the foundations of Lyft's service mesh architecture. We proxy all of our network traffics: HTTP, gRPC, Redis, Mongo, Dynamo, etc., etc. Envoy is capable of dynamically update its configurations without dropping the connections. And it also gives us consistent metrics across services, allowing us from the infra org to build standardized dashboards and alerts for all engineering teams. Based on what we have shown in the previous slides, last year we decided to extend Envoy to support the Redis cluster protocol. It gives us predictable failover behavior. We know the master always fail over to its replicas. It gives us replications, and it has very strong Redis community momentum. For the rest of this conversation, I'm going to call the sharded cluster of independent Redis nodes ring hash cluster because the word cluster is just overused. And I'm going to refer to the open source Redis cluster, just Redis cluster. The first thing we need to do to extend and support Redis cluster is implement some sort of service discovery. By service discovery, I meant we need to find out what nodes are there in this logical cluster. So we have to discover the list of nodes, the cluster slots they are responsible for, aka shards, and also for each individual nodes, whether they are the master node for that shard or the replica nodes for that shard. To do this, we need to specify at least one discovery host where we can use to send the initial cluster slot commands to discover the cluster topology. And after that, this host is not needed, and we will send all subsequent refresh by distributing it across all the nodes in the cluster that is discovered from the discovery endpoint. After we initialize and acquire the initial topology, we also needs to update the topology over time because nodes can fail, we can add new nodes or delete nodes in the cluster. So in Envoy, we provide 4 different topology refresh mechanisms, and these can be used in combinations. The simplest one is periodic. So basically, we set Envoy to periodically send the cluster slots and refresh the topology. This is useful and needed for things like picking up added replicas. And however, we have to be very careful about setting this refresh rate very short because it can generate a lot of load on the Redis nodes, especially if we have a large number of servers that are, or large number of proxies that are periodically sending these requests. The last 3 refresh mechanisms are what we consider adaptive topology refresh. They are based on the thresholds that we set for each conditions, and they are protected against a thundering herd of topology refresh by limiting the refresh intervals. So the number of redirects is easy to understand. It is basically the number of move or ask redirections response we get from a Redis node. Number of failures is simply the errors that we get when we're sending a request. And number of nodes degrades is a more advanced concept that is tied to the active health checking that we have in Envoy. And when a node either fail a certain number of active health checked or a certain number of failures, then we mark a node as degraded. In this case, we also want to be able to update the topology to see if a new node has been added. After we figure out what nodes are there in the cluster, we need to figure out how we are going to shard the request across all these nodes. And this is basically load balancing. For write, it's easy. We follow the open source Redis cluster protocol to calculate the hash slot, and with the topology information we have, we can figure out which shard the key belongs to. But what about read? Read is a little bit more interesting. For strongly consistent read, we want to send all of the read commands to the master node, because if we send it to the replica, it might be delayed because of replication delay. However, in practice, we often want to use the preferred master node. The preferred master read policy is different from master in that preferred master would send all the read requests to the master node as long as the master is healthy. However, if the master is degraded and there is a healthy replica, then we'll send the request to the replica. And this is very useful when the master node fails. And similarly with replica and preferred replica, the any read policy means the application don't care and it will evenly distribute it to all the nodes. However, it will prioritize healthy nodes over degraded or unhealthy nodes. With the same Envoy process, we can also set up multiple filters to listen on multiple ports for the same cluster. So an application can actually use multiple local ports to use different read policy. An example would be if servers serve both high priority and low priority traffics. We can set the low priority traffic to the Envoy port with replica-only read policy, so that we protect the master nodes from a sudden surge of low-priority traffic. In HTTP, we often use URL or header to determine which server to route the request. We like to borrow these very powerful notions to help us manage Redis traffic also. In Redis protocol, however, we don't have URLs or headers, but it is often the best practice to have prefix for different key spaces or different type of objects or different type of entities. So that's what we can use here also. So what we can do is we can borrow this concept of routes, and based on the prefix of the key, we send them to different routes, aka send them to different cluster. This is very useful for cache, where we can throw a lot of different services, each with their own key space, basically prefix for their keys, into a shared cluster. But when a particular feature or particular service is starting to generate a lot of traffic, we can migrate their key space into their own dedicated cluster without changing a single line of code, all through the dynamic configurations of Envoy. Once we have the notions of routes and working against multiple clusters, the next useful thing to have is have some way of mirroring the request across multiple clusters. This replication is done asynchronously, and the result of the mirror request is not used for the response for the downstream client. So we don't depend on it, but we just replicate it. So how is this different from the standard Redis replications? Well, unlike the Redis replications, the request mirror does not require the Redis node to join the Redis cluster. In fact, one of the clusters can be just a ring hash cluster. Another one can be a Redis cluster. More importantly, each of the cluster and each of the Redis nodes are not aware of the replica in this case, or the cluster that are being shared to. So there is no need for one-to-one master replica correspondence. You can have one cluster with 5 nodes, another cluster with 10 nodes. Also, because there is no master and replica, there is no replication buffer issues that could sometimes cause problems. Also, the standard Redis replication protocol is focused on the replication of data. This is focused on the replication of load. Of course, when we're using Redis replication, we also have the side effect of generating some write load on the replica. And similarly, when we are mirroring requests, we also have the side effect of replicating the data. In practice, with a reasonable TTL, most of the time, replicating the load over a sufficiently long amount of time is enough to replicate the data also. With the request mirror policy, we can choose to also exclude the recommends, such as the case when we are sending in here with the cluster denoted with a blue dot. Another configuration is the percentage of traffic we like to mirror or replicate. When we use this for migrations, we often ramp this up slowly and use this to fine-tune the load on the mirror cluster to ensure that it can meet the demands of the loads. Now here in this case, we are setting a 50% traffic, what happened when we turn the percentage higher than 100%? Now we have the ability to load test and stress test a different cluster with production traffic without actually impacting the production cluster. And this is a great feature. Next, we'll look at how we use these features in our migration flow. So, because the number of clusters we have is quite big, we would like to reduce the the burdens on engineers from different teams to migrate the ring hash clusters to Redis cluster. So we try our best to do this without requiring to change the code for the applications. So first, we provision the new clusters, and then we update the Envoy configuration to start shadowing traffic for both read and write. You might be asking, why are we shadowing traffic for both read and write? Isn't just write traffic enough? We just want the update to the cache, right? Well, we use this step to optimize the Redis cluster configurations to determine the number of nodes, the number of replicas that we need, and then we carefully monitor the stats during this step. We also want to ensure that the new cluster is operational ready so that we have the right alerts. We might purposely trigger alerts. We make sure we have the right dashboards, and we make sure that it is scale and failover works as expected. The next step, once we are convinced that the new cluster configuration is operational ready and can meet the scale requirements, we want to ensure the data is consistent across both the ring hash cluster or the old cluster and the new cluster. So we have a validator that runs just a simple script to compare values from both clusters. And we can open a new port so that the existing application is not impacted. And we usually run these replication steps for the longest TTL if the TTL is reasonably short. Like if it's 5 minutes, an hour, we can run it in replication mode and everything should catch up. However, sometimes when the TTL key is very long, say 10 days, then we want to speed it up by using the validator in a mode where it will copy over keys that are inconsistent. Now, at this point, you might be asking, well, like, what about some of the keys that doesn't matter how many commands you replicate would not get to a consistent state. For example, if you do increments, or if you are adding and removing things from a list. Well, it turned out most of the case it actually works fine as long as we understand the usage scenario. For example, very often even the TTL key the traffic would have a natural load where they will sync, and if not, the validator will catch that scenario. So third step is we just update the Envoy configuration to swap the clusters. During this step, we still want to do write to both. so that if something goes wrong, we can fall back to the old cluster and no harm will be done. And also sometimes the application is deployed across multiple ASGs. So rolling out this change can also sometimes take longer than expected, or sometimes engineer might forget that one or two ASGs that are writing this data, so we want to make sure they all match. And finally, we just update the configuration and stop the traffic to the old cluster. And then we can deprovision the old cluster. And now we have migrated from the ring hash cluster to a Redis cluster, or migrated to any other new clusters for that matter. With so many clusters that we have to manage and operate, the traditional approach of setting an alert and then manually respond to alerts are taking more and more of our precious engineering time. Very often, engineers would respond to this by grossly over-provision their cluster so that they don't have to deal with scale. Everyone thinks, of course, the service and the feature that we're going to implement is going to be a hit and we are going to experience massive scales. Other times, we have big events such as Super Bowl, where there will be a lot of traffic in a particular region, and we have hot shots. We used to need to manually run historical numbers to try to predict trends and pre-scale the clusters for these big events. As we all know, predictions are really accurate. And this manual approach is just not scalable. There got to be a better way, and this is how we started to experiment with autoscaling. Essentially, we have an auto-scaling job monitoring metrics and states of the Redis cluster, and this would replace a lot of our human intervention to scale up or down a cluster. The basic idea is simple. Scale the replica or adding replica for read, and scale the master or add shards for write. As we develop the features, we start to learn there's a lot of small details. Initially, we started with just using metrics, but very quickly we found out we actually need to get the role of each node to determine the correct actions. And this sort of information does not fit very well into the metrics system. We also found out that scaling replica worked only if the applications are using replicas for read. Some services, for consistency reasons, they send all their reads to master, so no amount of replicas that we can add would actually help. So we also need to determine the type of commands that are being used on each of the nodes, and ideally know the read policies for these services. Another thing that we learned is also adding replica is not free. It actually has performance impact on the master node also. The more replicas that we attach to master, the more network bandwidth that we use. So we have to take that into account. And of course, in a lot of in the Redis metrics, the amount of memories that I use for replications or the network use for replication are also not tracked. So we have to leave some buffer rooms when we're trying to add replicas. Another one is more of a limitations on elastic cache than on Redis in general is adding and removing shards takes much longer than simply adding a node or swap out a node for larger nodes. However, we are very happy with the speed in which we can add a new replica or just swap out the entire cluster and replace it with larger instance types. And here you can see this in actions. We have a cluster that was barely in use, and then traffic suddenly ramp up and it hits our CPU thresholds that we set for about 60% CPU for these clusters. And then our script kick off and a replica is added. However, you might notice that after the replica is added, we don't recover immediately. And there is a small slope from the replica is added to when we're fully recovered. That is because the new replicas are only picked up gradually with the periodic topology refresh that we have. So we have to tune this very carefully so that we can respond in time. Next, we'd like to revisit some of the lessons we learned using Redis as a cache for database. The basic idea is simple. First, we try to get the item from the cache, and if it's a cache miss, we read it from the database. Then we update the cache. If a hotkey was expired, then this pattern can result in cache stampede. There are well-studied techniques to mitigate this issue, such as locking and probabilistic early expirations. Normally, these techniques are designed to protect the database or prevent expensive computations. And the assumption is that the cache is available and the stampedes are triggered by cache expirations. But that is not always true. On Valentine's Day this year, our servers experienced higher than normal traffic because a lot of people are going out. This results in higher network traffic on one of our Redis clusters. Just so happened that servers had a bug where it would treat all Redis error as cache miss and would attempt to update the cache even when the cache miss was the result of a timeout on the get command. This vicious cycle of network timeout cause repeated sets on the same key in the cache, then it causes more replications network traffic on the Redis node to multiple replicas, which cause even more network throttled and more timeout, which bloated the replication buffer and increased replication delay and triggered the VG save and caused the Redis node to go into swap, eventually killing the node. So what are some of the lessons we learned from this incident? Number one, both cache error and cache miss will cause and should cause a database read, but they are not the same. Don't try to update cache on cache error. 2. Expiration is not the only cause of cache stampede. 3. In the cloud environment, network have both burst and steady state thresholds. And before we set our alarms, we need to benchmark each instance type very carefully. Similarly, for the write path in this scheme, we first write to the database and then we update the cache. Simple enough. But what happens if the update to cache fail? Then we have inconsistency between the cache and the database. This can often be easily mitigated with shorter TTL, but shorter TTL can impact hit rate. And also, shorter TTL means more explorations and more opportunities for cache stampede. Often, a longer TTL is desirable for when the database is down while we cannot serve any write traffic, we can serve the read traffic out of cache until the database recovered. However, cache stampede is not the only problems with this scheme. We can potentially have a race. So back to our read request. So we got a cache miss, we read it from the database. At this moment, another request, a write request, can come in, either on a different thread or even on a completely different instance. So we would update the database, update the cache, then back to the read request that would revert the value in the cache. Now we're back to inconsistent state again. Traditionally, we have two methods of solving this. One is using Redis transactions. The other one is using Lua script. Transactions works well, however, it requires a dedicated connection between the client and the Redis node. When we have an Envoy proxy in between, then it will be difficult and actually impossible for Redis to know which client is watching and watching the value. Of course, this is not impossible if we implement the proxy such that whenever we are doing a transactions, we give the client a dedicated connections. This complicated the proxy design, but it also prevents the throughput benefits of a multiplexing proxy. The transaction also have the disadvantage of requiring more read across the network to determine what to do after the transaction fail. Also, it requires the application code to have this transaction logic at potentially multiple places. The problem with Lua script, on the other hand, is Lua script can't and shouldn't check the database on what is the current value. And often, we want to use binary serialized messages or payloads, such as protobuf or message pack, or compressed payloads, so that we have memory and network bandwidth efficiency. So what would be a good solution then? If we take a step back and requiring the database results to have some sort of revision ID that are incrementing, then we can actually dramatically simplify the Lua script. So if we have a revision ID, then we can store the revision ID and the value as a hash in Redis. This would make it simpler to manage the TTL than storing the revisions and the value as separate keys. So we got cache miss, we read from database. Now our racing write comes in, we update the database, we use the Lua script to update the cache. Now we know that it's revision 2, and the Lua script update from the read path would be a no opt because the revision is older than what is already there. How do we deal with the inconsistency of the write path if the first Lua script update fail? Well, again, if we take a step out of Redis a moment, many modern databases have change streams functionality. So we can stream the changes to some streaming pipeline, and then the streaming pipeline can call a sync API on the code that is doing this update. And this sync would do the database read and then use the same Lua script to update the cache values. This way, most of the times, we would cause 2 additional read on the database and 1 on the cache. And in the failure case, we'll also issue the write, fixing the consistency issues. And you might have noticed we have separated DB proxy sidecard out from the applications. Why are we doing that? Well, this way, with the sidecards, we can support multiple languages and encapsulating all these logics. So if we have any bugs like the one we found before, we can easily fix it in one place versus having to fix it in multiple languages. And this also made it easier to implement the sync API for the stream service to call. Looking ahead, here's the list of features we're most excited about implementing. Envoy fault injections, I believe we have talked about it here before, and this will be very helpful for cases like our Valentine's Day incident, where before Valentine's Day, we could inject either error or delays or both into our production traffic and discover the bugs early. The Envoy fault injections, we can also scope to specific commands. So this is actually very close to being done. The PR is already out. It should be through the review process any day now. The next thing is also what we talked about earlier, having support for private connections. This is not limited to transactions, but also for blocking calls, we need private connections, and for pub/sub. Another item that we would love to work on is to support more cross-slot commands. This has been a lot of demands for supporting more cross-slot commands through Envoy proxy, so we'd love to do that. And another feature that is often requested is having some sort of request tracing support. For Envoy, when we use it as an edge proxy, it would issue a trace ID or some sort of request ID, and it will be propagated throughout our entire in our entire infrastructure, so that we can know for each request how much time is spent in each service and each subcomponent. We'd love to be able to extend that to Redis. However, Redis does not support any sort of headers in its protocol. So what we have to do is we need to have a Envoy proxy specific command that the proxy can understand, and then that will set the trace ID on the downstream connections. And from there, we can then emit the span for each of the Redis commands. And then we can have another to unset the trace ID, or maybe another request coming can override the trace ID. So we can have end-to-end tracing for all of our different tiers. And finally, we are excited to support Redis 6 as Redis, or working on supporting Redis 6 as Redis 6 become GA. That's all I have for today. Thank you. And if you have any questions, feel free to reach me on my email, and I will encourage you to check out Envoy. And if you have time, then you should consider participate in the Envoy open source project. Thank you. Bye-bye.